Welcome to springlib.
Okay, in order to draw this out, we're going to have to make some simplify the drawing a little bit. So our substrate I will be drawing as this with an R for the rest of the molecule. So here R will equal this part of the molecule, which doesn't come into play, where pH stands for phenyl, right? All of the reactivity takes place on the bromine and the carbon the bromine is attached to, essentially. Okay, and the other sort of abbreviations is that we know that this contains or has to do with aspartate or aspartate, right? And rather than draw the entire aspartate molecule, we'll just draw the oxoanion portion, right, which we know to come off of aspartate, right? So here, the ASP is representing the fact that the rest of this oxoanion or carboxylate is attached to aspartate. Similarly, for histidine, we know histidine is involved, but we don't need to draw the entire histidine molecule. So we'll just draw the side chain of histidine, similarly to how we've drawn aspartate, namely the part of the histidine that we're interested in. Right. Is this portion, right? And so we'll draw HIS to represent that's the rest of the histidine, right? So these are pretty much the parts of the molecule that matter. And so in this mechanism, which I'll start below this line, the bromine basically is going to get pulled into or held in place by some sort of halide binding site, right? So that's what's holding bromine in place. So I'll use HBS for halide binding site, right? And that nearby, or at least accessible to this location on this enzyme, is going to be a histidine, right? And what this histidine will do, right, is this histidine, which I will draw again, just a portion of, like we said, is basically going to hold the portions of the other portions of the molecules that we'll need, namely a water molecule, right, through hydrogen binding to that nitrogen. Right, we know we're going to need a water molecule. And the histidine will also be holding the oxoanion portion of our aspartate, right? Again, through hydrogen bonding, right? We know that this nitrogen has a hydrogen, and that will be hydrogen bonding to our aspartate, like so. Okay, so essentially then what happens is that this negatively charged oxygen performs SN2. Oh, sorry, and then this is, of course, right, going to histidine, the rest of histidine. This aspartate oxoanion will attack the carbon, which contains the bromine, right, which is going to force a backside attack, right? So we'll end up with then something like the following. Right, where this oxygen, then we know is still attached to the aspartate, right? And that nearby, let me make myself some space here. I drew the second step too high. And this is still the R, that's still the rest of our substrate. Right. But then nearby, we still have this histidine with a water molecule attached, right? Or, attached in the hydrogen bonding sense. And that the rest of this reaction takes place like so. It's basically going to be release of this portion of the aspartate. It's going to be release of aspartate from our substrate. So what's going to happen is that this water molecule is going to attack the carbonyl carbon of the doubly bound oxygen of the aspartate. And this is a multiple step reaction, but what happens is that the double bond pushes up onto the oxygen as a lone pair. And in the next step, that lone pair pushes back down to reform the double bond and kick off the, basically kick off our substrate, right? So you can show this in one step, you can show this in multiple steps. I will draw a diagram of what it looks like down below. Right, so you're talking about this is the general outline of that step. Something like this. You've got your ASP. Water molecule. This is how it would look in two steps. Then you'd have a proton transfer of a proton from this oxonium ion. We could draw that explicitly here. Technically, it would be mediated by a second water molecule, but it's most frequently just abbreviated in this manner. Then this would push down to reform the double bond and just kick off basically our substrate, releasing the substrate. Like so. Right, at which point the substrate is negatively charged. And if we want, we could show a final proton transfer step to the actual substrate from the, I guess, acylium cation here. Finally, restoring the aspartate and giving us our then neutral substrate. So all of this, basically everything in these three steps, is essentially, just trivial basic organic chemistry of attack on a carbonyl and release of the substituent that it originally had. Right, water attacks, pushes the double bond up, proton transfer, double bond reforms, kicks off the, in this case, our substrate, and then there's a proton transfer from our substrate, from the acylium cation to our substrate, giving us two neutral products. And that's what is represented by these four arrows being shown in a single step here in red. Everything in this box is basically, most frequently at this level of organic chemistry, just abbreviated with those four arrows. So in terms of actual like enzyme activity, really this is the only these are the only two important enzymatic steps because they show why it's important that a histidine molecule hold an aspartate ion nearby and keep it as a anion through hydrogen bonding. They show how a water molecule, which is also necessary for the reaction, is held nearby. And the importance of our halide binding site, right? So this is sort of the important enzymatic activity. This is like a final step that does rely on the water molecule being held nearby by the histidine, but the details of this particular transformation at the end are given here, but are also, somewhat ancillary, not that important. These are mostly just a bunch of proton transfers and basic organic chemistry.